So I'm actually a PhD student undertaking a PhD at Melbourne Uni, but I am based at the Commonwealth Research Institute. So CSIRO actually stands for Commonwealth Science and Industrial Research Organisation, and I've been undertaking most of my research there, where I am attempting to build an autonomous system for optimizing reactions over our catalytic static mixer systems. So for a case study, I'm essentially focusing on hydrogenations, which are a very common reaction in industrial processes and in research, and as it provides a very useful transform for simple molecules and even complex molecules. So these are common in a lot of synthesis schemes, but one of the main challenges is that they can produce quite toxic side products, and especially if you're using a direct hydrogenation, it can be rather dangerous to do them in batch. And as a result, there has been an increasing amount of effort to convert these into flow systems. So flow systems allow you to have a lot better control over your reaction process, and they prevent the requirement to have large volumes. You can have a small reactor system, good control, and thus mitigate the production of toxic side products, as well as increase the safety of dealing with hazardous gases such as hydrogen, so you can perform them a lot more safely. The traditional way of doing these systems is to use a packed begged reactor. These have a lot of issues when you start trying to scale up, because you have pressure and thermal drops across the reactor. You can have, when you're trying to scale them up, you have complex fluidic systems that you have to consider, which can make it a lot more costly to actually scale these into an industrial process. So CSIRO a few years ago now developed catalytic static mixer systems which are designed to solve this problem. So essentially they use computational fluid dynamics and genetic algorithms, I believe, to design mixer systems that are specialized for the flow regime in which the reaction is going to be processed. So this allows the reaction to be performed without essentially no pressure or temperature gradients across the reactor system, which makes it consistent and easy to scale. The CSM systems are mainly focused on noble metals at the moment, because they were focusing on hydrogenations, but they're gradually expanding to take into consideration a lot more reactions and mobilization of various different catalysts. The CSMs are now, I believe, purchasable from Merck and Precision Catalysts. But what I'm focusing on was the optimization of reactions over the black sapphire reactor, which was developed by Precision Catalysts to perform these reactions efficiently and consistently on a research scale for laboratories. So why do we want to build a self-optimizing system? The main reason is efficiency. So you can do it a lot. These reactor systems do have quite a large volume, so you do want to minimize the amount of reactions you do in order when you're optimizing them. And there is a lot of these reactions are very common to need to be optimized when you're scaling them up for industrial processes. So we essentially want to increasing the efficiency at which we can optimize hydrogenations over these CSMs will have a significant impact on improving the efficiency at which a lot of the reactions we are performing at CSIRO, we can scale them into industrial processes. So the system I built in order to test the reactions over this CSMs in the black sapphire reactor is shown in this picture. So essentially we're using the Vapotech system to control flow rates of reagents across the CSMs, and using an inline NMR spectrometer in order to quantify the yields of the products. And the aim for this process was to optimize the space-time yields across the space-time yields for the reactor, and to do so in a manner that will minimize the amount of reagents that had to be used and the time at which it could be optimized. So to do this, the algorithm we chose to use is Bayesian optimization. You've already heard about it before, but if you know anything about Bayesian optimization, it can be quite susceptible to noise, and if you've ever used an inline NMR, you'll know that they aren't necessarily the most accurate method of quantifying yields. So what we actually started looking into was methods of increasing the resilience of Bayesian optimization to noise within the system. So the way we decided to do this was to combine the standard acquisition functions such as expected improvement with a space filling component. So this way, an experiment will only be selected if it has both a good expected improvement and is sufficiently far away from already conducted experiments. This helps the algorithm when it's fitting the models because it prevents the models that are fitted trying to actually explain the random noise within the system. Because random noise can essentially be modeled as a really short length scale perturbation, and when you use expected improvement typically, you can get sampling really close together, and then the model will start actually trying to model the system noise, and when it does that, the performance is significantly impacted. Oh. Yes. Sorry. Okay, so as you can see from these graphs, the space filling expected improvement is a lot more robust to system noise. So you can see on the right, the expected improvement takes a lot more iterations to actually stabilize onto the optima, because the fact that it's greedy and sampling when there's random noise, it will get on a essentially it'll focus in on a random experiment which isn't optimal, it's just better than it should be because of the noise in the system. So adding the spatial component essentially allows you to balance how well you're exploiting the system with how accurately the model can explain the data. So when the system is more noisy, it will default to more of an explorative strategy, but when you have little system noise, it will still behave as the expected improvement does, and you still don't get a significant drop in performance when you're on the noiseless data. It essentially allows you to make your system more robust by allowing it to perform more exploration when you've got noisy data and more exploitation when you've got noiseless data where you have strong confidence in what the responses will be throughout the domain. So this system was tested on a wide range of chemicals, but the one that we compared to literature sources on a similar CSM system was for nitrotoluene. And as you can see from this graph, we actually weren't able to achieve the same space-time yields as the literature source. But the only reason that this was the case was because we had to use low concentrations of the substrates because of how long the reactions were taking. We had to use low concentrations in order for it to be materially efficient. Otherwise, we'll be using 10 grams, and that's not particularly desirable, especially when we're just testing the system. But as you can see, when we actually adjust the concentrations to be at the same as the literature source, you get considerable improvements to the space-time yield by, I believe, a factor of like 1.5. And this was achieved with lower reductant concentration than the source, as well as slightly milder temperature and pressure due to the system limitations for our optimization. Now this was isolated yield as well, so this wasn't using the NMR measurements. So we isolated 6 grams of the nitrotoluene, the toluene, in 50 minutes. And that was purified and quantified. But the system works on a wide range of chemicals. The NMR is fairly versatile, if not accurate. So you can quantify the yields of most simple molecules. And the system was able to optimize the majority of reactions we tested relatively efficiently. And the optimas were located within 20 experiments for each of these. And as you can see from the graph over here, the space-time yields were typically improved by a factor of approximately an average of 150%. But the optima was found regardless of the performance of the training data. So you don't get, for the reaction 4, you didn't get much improvement, but that was purely because the experiments that were conducted in the training set, which was Latin hypercube sampling, just happened to be really close to the optima. So you can't get much improvement. But even when the training data was poor, it would still optimize and find the optima relatively efficiently. So the system was relatively simple, and so maximum temperature and minimum residence time were determined to be optimal, which is kind of what you would expect from these systems, because kinetically, temperature is going to force this through a lot faster, and we weren't going to sufficiently high temperatures that we would get sufficient side reactions for it to be noticeable. Minimum residence time is obviously expected because we were doing space-time yield. The main reason we did space-time yield instead of other methods that are typically used, such as yield, is because this is a large system, as I said. If you do yield, it's going to obviously want to do longer residence times, which is not desirable when you've got a system which is 300 milliliters. It will take approximately an hour to do those ones. So we wanted it to be efficient in the optimization process, so space-time yield was a lot more desirable. For pressure had little impact, but that's kind of expected considering it was a transfer hydrogenation. It's also possible that the back pressure regulator we were using for this system couldn't handle mixed phase systems, so we were generating CO2. So when we were getting high conversion of the ammonium formate, that impacted the performance of the back pressure regulator, and so it wasn't particularly accurate when you were getting high yields. So when we were setting high pressures, and if it was at high temperature, so we're getting good conversion, then the bubbles that are produced would result in the back pressure regulator losing pressure, so everything was pretty much at 1 or so bar, even when we were setting it higher. An interesting thing that was noticed was that the ammonium formate concentration, the optimal amount, was quite dependent on the substrate. So for the nitro compounds, quantity approximately slightly above 4 equivalents was optimal in most situations, which is quite consistent with what you will find in literature sources for these reactions. However, for the chloro one, it required it maxed out the ammonium formate concentration, and that is because you're also getting dehalogenation, and so that would be also competing for the hydride source on the surface. An interesting fact, so this is basically essentially demonstrating the effect of the space filling component on the exploration strategy. So for the methoxystyrene on the left, the concentrations of the product could be quite accurately determined by the inline NMR. So the algorithm was a lot more exploitative, so you can see that it remained at maximum temperature for most of the experiments and minimum residence time. But for the nitrotoluene, the accuracy was significantly lower due to interference with other peaks in the system, and so the algorithm was a lot more explorative, but you still get the majority of experiments were still at the higher end, though there was a lot of exploration of lower because the interference was making it harder for the algorithm to determine what factors were impacting what. So to sum it up, the system could successfully optimize all the reactions that were explored, and could do so in typically under 25 iterations. And even when the NMR was not 100% accurate, the system was still able to converge on the optima. And obviously, since it was all automated, it required minimal labor. I could just press go in the morning, leave it the day, and it will have the optima by the evening. So, yes. I would obviously like to thank my supervisors for this, as well as CSIRO and the Australian government for funding this project, as well as everyone in the Polyzos Lab research group who helped me, especially with the chemistry, because I have slightly more of an engineering background. So, and also thank you for allowing me to present here. It's been a pleasure and I've enjoyed the talks. So yeah, any questions?
Any questions?